Welcome to a new tutorial, now with questions about computer architecture, which is lesson 4. But before we start with this, I want to come back to one thing which was not completely clear in the last tutorial, and therefore let's have a short review. Use your truth table from question 3 to also create the conjunctive normal form. So if we have a look now again onto our truth tables. So I got some question about that because I was a little bit lazy, and if you watch to the positions, the decimal positions 10 to 15, there is a cross, so I did not take care in that. And the question was, or the feedback was, that if you want to do the Kano-Weich diagram and the conjunctive normal form, things like that, then you have to take care also on these positions. And you're right. So if you want to do a complete set, then you have to continue. If you reach the decimal 10, then the ones position in the base 10 system again is 0. So the 7-segment display should show 0 again. In 11, you should have a 1, 12 a 2, 13 a 3, 14 a 4, and 15 a 5. So therefore, you should have also some truth table values at the positions from 10 to 15. Especially if you make the conjunctive normal form. In some cases, in some of the tutorial questions, I set these things to 0. So I set the positions from 10 to 15 to 0, so that you have a nice situation where only from 0 to 9 you will have illuminations of the LEDs, and from 10 to 15 you have nothing, you have no LED at all if you use the disjunctive normal form. In the conjunctive normal form, if you want to do exactly the same, of course you have to define the 10 to 15 also with 0, with the output 0, so that you get this. And then you can of course make your Kano-Weich diagram in both situations. So I just showed in the tutorial and also in the lesson how to do this with a disjunctive normal form, but of course you can also do it with a conjunctive normal form. So I can show you this, and I can also show you the complete set, so that you understand that what is shown here is not completely true. It's only true if you have just the focus on numbers from 0 to 9, and if you forget or don't take care on the rest, like here marked with the X. So let's have a look into the situation like it would be if you do a complete setup. So in this case, on the left side, you have the disjunctive normal form and the Kano-Weich diagram for this. On the right side, you have the Kano-Weich diagram for the conjunctive normal form. So the big difference is that in the disjunctive normal form, you collect the ones. So you collect blocks with the ones. This is in most cases easier because you just check the participating inputs, and then you combine them with and you combine all of these blocks with an OR. So that the complete setup or the complete terms look like this. On the other hand, if you want to do a Kano-Weich diagram with a conjunctive normal form, you collect blocks with 0. And here now you have all of the zeros. So in my sample, I set everything starting from 10 to 15 to 0. And then you have, of course, here all of the zeros, so that the left and the right part are equivalent. And then it's a little bit different. Now you check which elements do not participate to this block. So for example, you have not an A naught, and in this case you have not an A naught and a B naught which participate, and then you combine them with an OR in this case this block is A naught or C naught, because the elements which do not participate, which are not part of this block, the inputs which are not part of this block, are A naught and C naught. And then you combine all of these terms with an AND, so that you have on the right side this and on the left side this. This is the simplified version of the disjunctive normal form, and this is the simplified version of the conjunctive normal form. If you do not take care how many inputs your different gates have, then you have really the same number of elements, because you can reuse existing negated inputs, so that in this case you have a setup like this, and in the other case you have a setup like that. So combining, you have 4 negated inputs each time for both situations, and then you have 4 AND and 1 OR here, or 4 OR and 1 AND here. And if you compare this, then you have exactly the same number of gates, so that you have a simplified version even if both look different. So therefore these simplified versions are the optimum, so you cannot simplify them furthermore. The thing which you find in the tutorial, so the version where I only take care on the 2 elements, like the 1 and the 4 in the case of the A LED, and where I just take care on these 2 numbers, just works if you have inputs from 0 to 9 in decimal. And if you have larger or greater inputs, then this is not equivalent to that or that. So again, if you want to have really the same, so if you want to take care of all of the inputs, then you have to do, of course, all of the terms for all of the 1s or 0s, either for the disjunctive normal form or for the conjunctive normal forms. And of course, usually if you want to do a real world scenario, so like shown in my sample, where all of the numbers are used, so that you have 2 7-segment displays, one for the 1s and one for the 10s, then of course you have to take care on all of these inputs, and you have to continue from 10 with 0 in the 1's position, 11 is 1, 12 is 2, and so on, and on the 10th position you have the 1 all the time. And with this you can continue, of course, and can also set up larger 7-segment display combinations, so that you can take care on larger numbers, on representations of larger numbers, or you just jump over to something like an LED matrix, so that you can represent whatever you want. I just wanted to come back to that, because I had this question, and it was interesting to show you all of these things again, so that you might get a better feeling that you have done everything right, if you take into account all of the inputs. Okay, so let's come back to our tutorial for today. Our tutorial for today takes care on the computer architecture things, and we started with the ALU, with the arithmetic logic unit, and you can find this ALU in the download area for Logisim so that you can do some simulations. And if you do this, then you can play a little bit with these possibilities. So you can add numbers, you can subtract numbers, you can do increments so that you learn what you should do. So set the data, set the control word, pull a clock, and then you get the result. So let's do this. The first question uses this ALU for adding numbers 0f in hex and 07 in hex so that you get the result. So let's directly jump to Logisim. So what we do is we first of all set the numbers. So we have 0f, which means we set all of the lower bits to 1 and the higher bits to 0, and we set the others to 7. So 7 is 6 plus 1, so 4, 2, and 1. So it's 7. If you really want to do the calculation as requested in the question, so that the first number is 0f and the second number is 07, then if you have a look at it, you will see that input data A and input data B are arranged like this, so that we should have here the F and here the 7. So this is the real replacement or the real set for the input of our question. And then we do an addition. So let's take care on what the control word is for an addition. So it's the first one. So we set 1, 1, 1, 0, 0, 0, 1. So now we have the data and we have the control word. And what we can do now is we can now set a clock pulse, and we will get the result here, which is 1, 6 in hex. And that's true because 7 plus 15 is 22, and 22 in hex is 1, 6. So let's go to question number 2. In this case, we want to subtract number 5 from number 3 and think about the use of the 2's complement. So we come back to lesson 1, where we learned about the numbers, the binary representation of the numbers. So let's play with this. So we subtract from 5 the number 3. Again, what we do first, we set the data. So we want to subtract the number 5 from the number 3. So input A is 3 and input B is 5. So if we now want to subtract, we subtract A minus B, 3 minus 5. And let's see what the result is. 1, 1, 0, 1, 0, 0, 1. So this is the control word for the subtraction. And then we give a clock pulse and we see that we get FE. This is the 2's complement of minus 2, because 3 minus 5 is minus 2. So how does this work? Let's go to the external camera and I can show you this. So if you remember, so the 2's complement continues like that. This is 0, and then we have the minus 1, so we have the plus minus sign bit, and the minus 1 is this, and minus 2 is this, and minus 3 would be this. So if you have this, minus 2 is this bit representation in the 2's complement, and therefore it's quite simple. We take a look onto here. So we have, in this case, we have 15, which is F, and in this case we have 8 plus 4 plus 2, which is 14, and 14 is E. Remember, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So in this case, in the 2's complement and with a sign bit, we have FE as result. So our arithmetic logic unit really processes a correct operation even if we change from the plus range to the minus range. Let's come to the next question. Increment number 7. So we want to increment by 1, and therefore we use the number 7 and we use the increment operation. So again, we set the input. Here you have to take care that the second input must be 0, because otherwise the simple ALU here will do some not correct things. So more complex ALUs will process the data correctly. So we want to set 7. 7 is this, and then we set the increment command word. Increment is A plus 1, so we have 1, 0, 1, 1, and 0, 0, 0, 1. We give a clock pulse, and we see in the output result that we have 7 plus 1. So we have an increment by 1. And then we go to the last question in this block. Create a specific result and compare shift left and rotate left. Shift left and rotate left are very important operations because they do multiplication by 2, and we can have a look what happens if you do the shift or if you do the rotate left. So let's do this. Let's do first of all a sum again so that we get a nice output. So we sum up input A and input B. Let's see what happens. And then we have this situation 5E. And now take care on the result here. So we'll do again the same stuff. And then take care on the result here what happens. First of all, we do the shift left. So let's set everything to 0 here. And then we do the shift left. Shift left means 1, 0, 1, 0, 0, 1, 0, 1 as a command. And then let's do the clock pull. So what happens is that we shift now the bits to the left, so that the bits will jump always one by one to the next position. So let's see. You see? And the result is that we shift everything out of our 8-bit block. So they disappear. And the result is we will have a 0 at the end. So let's set the same input again so that we have the result which we had before. Let's set 57 in hex and 7 here. And let's do an addition. So 1, 1, and the rest 0, and the last is 1 again, so that we get the same result which we had before. Let's set everything to 0. And then we set the rotate left. So rotate left is 1, 1, 1, 0, 0, 1, 1, 1. And now let's see what happens. What is the difference to just a shift left? So take care on this 0, 1, 0 pattern here. Do you see? This 0, 1, 0 pattern appeared again from the right. So rotate left means that the bits which disappear here on the left will be sent to the right again, so that we have a rotation here. So again, take care on this. Take care on this one. So the 0 now flows over and comes back from the right. The 1 flows over and comes back from the right, and so on. So that at the end we have again just a rotation here. And these two operations, shift left and rotate left, are quite important because you can manipulate data. For example, if you have input lines which you have to check, so that for example you can check if some switches are on or off, or if you have special error codes. It's often used in this case, and also for multiplication with the base 2. So multiplying with 2 is just shifting, and therefore you have simple tricks, simple methods to deal with these things. So let's go to the second question in our tutorial. The second question again is with Matlab. So we do Matlab programming again, and we want to play a little bit with this queuing, so that you arrange process tasks in a way that they are processed in a batch situation or in a round-robin situation. And then you can use this to play a little bit with it, so that you get a fair algorithm, or that you simulate situations like in a supermarket where we have different queues in front of the cashiers. Let's have a look. Write a program with Matlab to simulate round robin. Define the number of processes as a number of working processes. Simulation duration second, which is the complete duration time of simulation seconds. Time slice second, which is the time of one time slice in second. A vector runtime sec, with a runtime of each process in seconds. Maybe use a randomized set, so that you have different starting conditions each time, so that the processes last differently. And a vector arrival time, which is the arrival time of each process in seconds. Maybe also use a randomized starting situation. The first process in this set is the idle process. So if no other process is active anymore, this idle process will continue. The goal is to create a color plot where the runtime is on the x-axis, the process number is on the y-axis, and the color at each xy position shows if the process is active or inactive, or if it is waiting. Play with different start parameters and compare the results. Which quality parameters would you use to compare the results? So let's go to Matlab and let's open an editor. So we usually start always with the same commands: clear all, close all, and CLC, so that we get a version setup where we can do our programming. And then we can think about what we need. So we need, of course, first of all, the number of processes. So the number of processes, in my case, I define it as 15. So we have 15 different processes. which should be controlled in our simulation. Then we define how long our simulation will run. So in my case, I define a simulation duration in seconds of 20, so 20 seconds in total. Take care that I always use this ANSI style or camel case style, where I also start with an uppercase letter at the beginning. So if you look, each separate word, for example, in the variable name is started with an uppercase letter, so number of processes. So it looks like a camelback, and therefore it's called camel case style or ANSI style. And then we want to define our time slices. So how many or how short operation step will be. In this case, we take into account that our operation in total, our selection mechanism in total, will cost almost no time, so that the time slice or the waiting time is exactly our time slice, so that our selection mechanism itself will not take any time. It's not true, of course, but for the simulation it would be good enough. So what else can we do? Before we start, we have to think about how we organize our data. You already have seen a little bit of this in the exercise task, or you have hints there, but let's think about and let's discuss what we want to do and how we want to proceed. So I change to the external camera, and then we will see what to do. So we can define a vector which contains our arrival times. So in my case, I have from 1 to 15. Each position defines the arrival time of a process. So that, for example, if I have 0 here, then it defines that it comes into a selection mechanism at the 0 second. If I have 1.5 here, then it defines that it comes into the selection mechanisms after 1.5 seconds. So, and then we can define another vector. Of course, you can do it in different ways. I do it separately so that you see the different meanings with a runtime. So this vector defines exactly for the same processes how long the process will take time to do its job. So for example, if we have 5 here or we have 1 here, then it means that this process arrives at the 0 second of our simulation, and it will need 5 seconds of operation time. And in this case, it arrives in 1.5 second of our iterations, and then it needs 1 second of operation time. So this is our definition of processes. And then we need an overview about what is the current situation. So which processes are already in our simulation, so which processes are currently or available to be active. So for example, we check this process would be active, and then we set here just the time which is still remained to process this task. So this is the current situation, which I call process table. This is also in operating system called process table. It contains much more than this. What I have in the process table, it also contains the line of the code where it will be continued, things like that. So in my case, I would have here 5, because it starts at the beginning. So I define a starting situation, and it starts with 5 seconds, and then each iteration step it will reduce this time by the time slice. And then we will create the simulation history. The simulation history is a color plot. Color plot means it's a three-dimensional plot where we have an x-axis and a y-axis. In my case, the x-axis is the number of iteration or the current iteration, and this is again the process number. And then each position, so if we have the first iteration, so each position here defines with a color code what the process did. So for example, if the process was not active and did not wait, so was not ready for operation, then we have a special color. So if it was waiting, so for example in this case, if it is already appeared, or if it already appeared in our iteration mechanism, then it is in a waiting state, and if it is active, then it has another color. So with this setup, I can define per iteration step, and from iteration to iteration we have exactly the time slice, or the delta t here. So delta t, at each operation we have exactly this time step, and after the number of iterations we have, in our case, the 20 seconds interval, so our complete simulation time. So what we now do is, or what we need, you see, we need something like a loop which iterates through this thing here. So this is our loop. This is our round robin mechanism, where we can do different selection mechanisms. So in principle, this is the time, this is the number of processes, and which process is active, or the state of the process is defined with a color here in this code. So this means this is our history of processes. In my case, I name it operation status. And it's a matrix with number of iterations in the columns and number of processes in the rows. So and then we have to think about what we want to do. So how this program will look like to create such a table, or such a table set. So in my case, I first of all have to define the starting situation. So we define the starting situation, which means we define how these runtime and arrival time look, and then we create a first set of the process table. So this is process table at state or time 0 seconds. So this is our starting point, and then we have to decide for the starting point which process is active. So which is our process, our selected process. So I call this find first active process. We can make a parenthesis around this first, because you will see that during the whole loop, or the whole round robin loop, we'll always come to this situation that we will have to find the next active process. So it is find active process. So I would call this selection mechanism, and this selection mechanism is different for the different versions of our selection. So for example, if you have a preemptive selection or a batch selection, things like that, then we will have it in a different way. And then we have finished our initial starting condition. And then our loop starts. So we have now our round robin loop. And what we do is we always have to adapt the process table. So that, for example, if new tasks arrive, that they appear in the process table. So according to incoming tasks. And then we'll have to do a selection or a conditional behavior, because if there is no process active, we will have to run the idle process. So if the idle process is required or active, so yes or no. If it is active, then we just do the same what we did here. So let's call it A, find next active process. So it searches the next active process. So it's the same selection mechanism like here, and as long as there is no process active, we'll keep the state of the idle. So the idle process will be operated. The next thing is if another process is active, so if we can run another process, then we put something into our history. So in this case, we write something into the history. Of course, this must be done also here. And then we reduce the runtime of the current process by the time slice, because it's operated. So this is the simulation of the operation. So this is our simulation of the operation of the process. And then we do exactly the same what we do everywhere when we want to find the next active process. So we search the active process. And after we finished, so we run this number of iterations. So we have to calculate the number of iterations. This can be done by the simulation time. I call it simu time, divided by the iteration time, which is the time slice. And then we get the number of iterations. And if we finish our loop, then we can plot the data with this P color plot. So this is what our program should do. And this is what we want now to program. So let's change back to our Matlab. So first of all, we want to calculate then the number of iterations which we need. So we divide the simulation duration in seconds by the time slices in seconds, so that we know how many iterations we will need for the whole simulation. And then we create all of the matrices which we need. So if you remember, we want to have the runtime. In our simulation, our case, I would say we will have a first start point that each process needs exactly 1 second. So therefore, I create a matrix with a number of, or a vector with a number of processes, and each element has the value 1. So it's exactly 1 second in our iteration. And then we also define an arrival time. So in my case, I say all processes arrive at the beginning of our simulation. So I define a vector with a number of processes, which has everywhere a 0. And then I have to reset the definitions for the idle process so that it is not taken into account, so that I can do a special behavior for this idle process. So it will not be found by my search algorithm or by my selection algorithm, because it is always 0, and it will be available the whole time. So in my case, it will not change anything here, but for later on, if arrival times will change, then it will change things. Okay, so what else do we need? We need, of course, the matrix for the history. As I said, I name it operation status, and as my first selection mechanism will show the batch mode, so I call it operation status batch. And then finally we need the process table. So in my case, process table is a vector with a number of processes, and with everywhere is a 0. So if you go back to the drawing of our simulation, then you see that we have exactly defined these parts here. So this is the matrix with a history. This is our process table. It's a vector with, in my case, 15 elements. And I have 2 vectors with the arrival times and with the runtime. So it's exactly what we defined already now. And now we have to fill the process table with a starting situation. So I do this with this for loop. So I just run through the arrival times and check if it is 0, so that the process arrives here at this time, so at the starting time, which is 0. And if there is a process active, so if the runtime shows a value, then I put it into the process table. This means, in my case, with this loop, all of the processes are activated, because all processes start at the arrival time 0 and will have a 1-second runtime. And then I have to find the first active process. So this is quite simple, because I just run through my process table. So I define the current active process index, and I run through my process table. I can start here in process 2, or I can start in process 1, because I defined the runtime of the idle process with 0. So it doesn't matter in this case. I can directly run through all of this stuff. And I just check if there is a process in my process table, so in my vector called process table, which has a runtime greater than 0. So I run through this, and then I get an index, which is my first active process. So this process will get the acceptance to be processed. And then I do nothing more than a loop. So I already know, for example, how many iterations I need. So these iterations I calculated here, and then I go step by step through these iterations. Then I see which iteration is currently operated. I do a small output, so that I get the iteration number of the total number of iterations which is required. And then, do you remember? So let's go back to the external camera, what we have to do next. So we have to do next these things here. So we adapt the process table according to new incoming processes. And then we do a selection, idle or non-idle, to do the next steps. So this is exactly what we want to do now. In a first step, we check if there are new incoming processes. So in our case, it will not have any effect because there will be no further process because all processes are activated at the time 0. So active processes can be selected if they arrive in the time for the iteration steps of the previous and the new iteration step. So I calculate the iteration step, the previous iteration step, time slices, and the current iteration step times time slices, which means if a process arrival time is in between this interval, then I know that the process should be started now. And then I set the time in my process table, so nothing more. So I just bring the process into a state that it could be activated. And then we have to do this separation between the idle process and a non-idle process active. So if the current active process is not 1, then it is a real process. If the process is 1, so else state, then it is the idle process. So if the selection mechanism came to a situation where it is 1, and if you check this, we start from 2, but if no 1 is selected, the current active process is 1, so we'll automatically select the idle process. Then we will do this idle processing. So let's first of all also focus onto this idle processing. So here is the idle part, and here is a real process part, or non-idle. So in this idle process, we first of all set the history so that for the individual iteration step, we set the idle process as active. So in our operation status batch, which is this matrix where the iterations are on the columns, so on the x-axis, and the number of tasks or number of processes on the y-axis, we set the 1 and iteration step to 2. So we set process 1 to 2, and 2 is my definition for active. So I define 0, it is not ready for operation, 1 it's waiting, and 2 is active, so that we can define different colors. And then we do nothing more than what we already know from here. So I can directly copy this to select the next active process. In my case, I always start again from the index 1, or index 2 in this case, which means that I always search the next process with the smallest number, which is active or ready for operation. And this is already what I have to do if I'm in the idle process. So I set the current status, which is just a thing for the history protocol, and then I select the next process, which might be active. So let's jump to the operation of other processes. So what should we do here? If we go back, we again set the history. So it's similar what we have already done, just with other process IDs. Then we reduce the runtime of the process so that we simulate our operation of the process, and then we search the next active process. So it's quite simple. We do the following steps. We set our history. How do we set our history? So we run through all of the processes. In this case, we can start from process 2 again, because it's not the idle operation. And then we can have a look. If the process count is the current active process, we set it to running. So it's the same what we did here. So I will also copy this to here. So it's already running. And if it is not running, and if the runtime in my process table is greater than 0, so that the process is already in my process table and requests for time of operation, then I set it to 1, which is waiting. So I have 0 non-active, 1 waiting for operation, and 2 is running. So this is the definition or the setting of our history table or our history matrix. And then we decrease the active process. So it's exactly the step which we defined in our runtime model. We decrease the runtime according to the already processed time. So what do? We subtract from this current runtime in our process table the time slice, so that we each time when we operate this stuff, we reduce our processing time by 1 time slice. And then finally we do exactly the same what we want to do for the selection. So this means we do again a selection mechanism. So that this is exactly the same what we know here, with one small difference, and therefore I made it explicitly here, even if this command does not do anything, just that you see that there is a small difference to all of the other scenarios. If in the batch mode a process completely finishes, so if the process comes to a processing time or runtime of 0, then I just do the selection of a new process. Otherwise, I will keep the process active which is currently active. So you can skip these 2 lines, of course, but it just should show you this explicitly, that the selection mechanism just starts if the process already finished. So remember, batch means we start a process, we finish the process, and after finishing the process, we continue with the next one. So this is already almost everything. Let's do also almost realistic timing. So therefore, we just set a timing parameter, which is exactly the waiting time of the time slice. So we guess that this, what we have here, does not take any time. It's so fast that we don't take care of this. So we'll have, it's not really true. It will have a little bit of shifting here. But in our case, this is the operation time for one process, and therefore this is our time slice. So that our process simulation will now run 20 seconds, and it will processes our selection mechanism. And finally, we just do a plotting. So I prepared everything so that I just have to copy it. I do a p-color plot here, so I don't explain it in detail. You will see the result. It will do a plotting of our simulation. So again, what did we do? We defined our starting parameters. Then we created all of the variables or matrices which we needed. Then we did our initial startup condition setup, and then we started with a loop. Each loop does the same. It brings new processes according to their arrival time in our process table, and then it selects is the idle process active or other process, and then we do different things. We always set our history. Then we decrease the runtime. If we are in normal process mode, and then we select a new process. And the same we do in the idle process, so we don't have to reduce the runtime because it has no runtime. It's always active if no other process is active. But we will search for new incoming processes which might be active. And then we do the plotting. So let's play with this. I will set it in this way so that you can see the runtime. And I will start the program. So what you will see, it runs now through 2000 steps. This 2000 steps comes from this division of the simulation time by the time slices. And then it will run about 20 seconds. And after 20 seconds, I will get a plot. And you will see that this plot exactly shows what we expected. So all arrived, or all process arrived at the first 0 second. So we have all of the processes here, and then the first process was selected for exactly 1 second, the next process was selected for 1 second, and so on, so that we have a batch mode. And you see, according to this color here, that one process is already waiting about 14 seconds until it is operated, because it is in the queue, and until each process which is in front of this process, so which is in the queue ahead of this process, is not finished, the process will not start it. And then we have this batch mechanism. Now you can of course play a little bit with this stuff, so that, for example, you change the arrival times here. For example, that you do a simulation with a little bit of, let's say, randomized arrival times and things like that. For example, if you want to use this randomized setup, we can replace these things here with a randomized process, so that we use randomized setups. In my case, I made some specifications so that process arrival times and run times behave in a special way, so they do not start later than 15% of our simulation, and so on. So let's run it in the same style again, and you will see another behavior. Again, we run through 20 seconds of simulation time. We'll do 2000 steps, and after 2000 steps, according to our randomized arrival times and randomized, let's say, run times, we will have a special behavior. So let's have a look what happens now. So now you see that the processes arrive in different time intervals. So, for example, a few processes arrive at the first 0 second, another process arrives at the first second, and then you have different run times. So, for example, in this case, you have a runtime of about 5 or 6 seconds, so that you see the waiting times. So, one process arrived early and finished early, other processes started then, and then it continued here, so there was a small waiting time until this process was finished, and then it continued here, and you see some processes which would have just a very short time of processing will have to wait a very, very long time. So it's not really fair in some cases, but you have to define what is fairness here. So this means you have to identify how you want to treat processes. In my case here, the processes are treated according to a special priority. Do you see the priority? I always start here. So I always run through the process table according to the process number. So the process number is in principle already a selection mechanism. So it's already a prioritization of the processes. And therefore it means that we already have something like a prioritization. And therefore we have to take care of this. So what is fair here? Do we want to search the next process here which has the shortest time? Then we have processes with longer times which have to wait the longest time period. So it's unfair for them. If we process longer processes first, then it's unfair against the shorter processes. So each selection mechanism will have some fair and unfair characteristics. And therefore it's not so easy to give a fairness here in this selection. And therefore you will now see what the preemptive style does. So the preemptive style gives any process a chance to process data, and it will directly work on the short processes because they will finish earlier in this case, because they will be operated in time slices, and if they finish, they're finished. So it doesn't matter, so that the longer processes will have a more social behavior, so that they spend a little bit of their time for the others, and therefore each process reacts like a little social character, so that others have also the chance. But in any case, later on, it is again in some situations not really fair. And you will always have a situation that they're dedicated processes, like interactions with user or something like that, which must be prioritized, because the user does not like to wait until something is finished. So the next step will change our program so that we will have another selection mechanism, so that we will do the time slicing. So let's have a look at this. So what do we have to change in this case is, in principle, we have to change our selection mechanism. So in this case, find the first active process. This selection mechanism must be changed. Let's have again a look onto our diagram. So if you search here where we did the selection, that these positions, and this is also would be an ideal way to make your functions, because it's always the same. So a function could be called, but we have to change this. Search for active processes. So I'm a little bit lazy again, and therefore I not change all of the search mechanisms, because, for example, for my starting initial situation, I can keep this because there is no process active at the moment, so I do not do a selection according to the runtime or something like that, so that I have a prioritization. I use the same prioritization which I already used before. So I take the process ID, the first process ID which is active, I will take. So the initial situation I will keep, and I also keep the situation for the idle process, because in my case, if there was no process active, it's again like the initial situation, so I take the next one. So what I'd like to change is this part here. So this search if a real process or another process is active. So first of all, let's jump back to have the starting situation where we have no randomized set. So in this case, I keep my randomized set and just replace it by the non-randomized situation which we had before, so that you directly see the difference if we now do the round robin with a preemptive setup. So I replace this again with vectors where a start time of 0 happens, and each process runs exactly for 1 second. And then let's replace the search mechanism here. So now it's a little bit more difficult, because if a process is active, we always jump to the next process which is in our process table and waits for activation or was already active. So therefore, we have to replace these things completely, and we do the following. We always jump to the next process. This means the next active process is the current active process plus 1. And if we reach a number which is larger than the largest number of our processes, so if we jump out of our process table, we start again with 2, with the next real process and not with the next idle. Okay? And then with this, we have to start our search loop again. So we'll need a loop which runs through our process table as long as I do not find the same process again. So for example, if I have an active process with ID 2, no other process is active, and ID 2 will continue work, so I will run through the whole process table, find the same ID again, and will continue with the same process. So that I can do this in an easy way. If I find another process where the process running time is larger than 0, I take this one. So that I have this round robin. I have a currently working process. I change to the next active process or waiting process, and so on. So that at each step I always get the next active process. If I have this, I will take the next one. If not, then I will go to the next process, and so on. So this is again the same what I did here. So I just continue here. It would not be necessary to have this else end here, but because we have this break here, break means we interrupt our while loop, but it shows that I have a different situation. I find a process which is active, or the next is not active, and therefore I search for the next one. And then we have one special situation again. The special situation is no process is active or waiting anymore. But of course, there can be in the future that processes will come in an active status or in a waiting status again. So that we'll have to change to the idle process, and the idle process will then select again if something is active. So therefore, if we reach the same process here, so I make it a little bit larger so I see it. So this is our selection mechanism now. So if after the while loop I end up with a situation so that the next active process is the index of the current active process, but this current active process is not active anymore because the runtime is already 0, so that there is no time left which the process would need, then I'll jump to the idle process. So again, I just changed the selection mechanism. This is the essential part. The selection mechanism is exactly that, what gives us a different behavior in our queuing mechanism. And then we just search all the time one next process, and we activate the next process in round robin version. So this round robin is defined by this. So if we reach the largest number of processes, we start with the smallest number of processes, so that we have really a loop through that. So let's run this. Remember, we changed here that we have the starting situation again at like in the beginning, so that all processes have the same runtime and start at the very first time. So do you remember? We had the situation that the processes were batched, so the processes were sequentialized, and process had to wait a very long time because other processes came earlier. And now let's start and let's have a look what happens now. So again, It runs now through our complete table and our iteration steps. We have the same number of iteration steps, 2000. We have 20 seconds of operation time, and then we will get our plot. And now our plot looks like this. So what happens now? It looks a little bit strange, but what happens now? The first process is active, the second process is active, third, fourth, and so on, running through all of the processes. And then the next one. So you see the first time period is filled by all of the processes. So you see this diagonals through all. So all processes now need the same time. So this is what I meant with the social behavior of this algorithm, because all processes now have a little bit of time, and all processes will finish at the same time in this case, because they all can operate their things and no process has to wait longer. So all processes will need the same time in the CPU. And after all process is finished, we have again the situation that the idle process continues. So the complete time which we needed here is almost equivalent to what we already had with the batch processing. So it's of course like that, because if you need 15 seconds for the whole tasks, then you cannot be faster. So you will need these 15 seconds. And these 15 seconds appear again here. So it's something like that. If you check this, you see that again we requested 15 seconds because we had 15 processes, and 15 processes where each process requested 1 second of processing time request 15 seconds. So in the batch processing and in the preemptive processing, we will have the total time or almost the same total time. But for the process behavior itself, or for the view onto each process, now it's completely different, because before we had a situation that the processes had to wait and then they were processed. Here now all processes are processed, and you see it if I go, or if I zoom into here, so that for example you see these different steps, so where the processes change, and each of these yellow parts here is exactly my time slice. And this is the nice thing to operate in a queuing mechanism, so that all processes get the feeling to work at the same time, to work in parallel. Now let's have a look how it is when we have this randomized situation. So let's go back to our randomized situation. We just comment out this, and then we have the randomized situation, of course now with different numbers, so that is not directly comparable to the previous one. If you really want to compare it, then you have to remember the different sets at the beginning. So for example, you do the stuff here outside of your script, and then you can operate different selection mechanisms on that, so that you can directly compare. Again, after 2000 steps, it looks now like this. So for example, there was no process at the beginning here, and then the first or two processes arrived, and the first one was taken. So there was the idle process, and the first one was taken, and then the second one, first one, second one, first one, which is here 7 and 10. So 7 and 10, 7, 10, 7, 10, and then other processes arrived. So 2, 3, 6, and so on. So then they shared the complete stuff, and you see short processes again finish earlier. Remember what happened in the batch mode. In the batch mode, there was no care on shortness of a process. So they were just operated when they are in the queue. So in this case, short processes end up earlier here. Of course, they're not as fast as they would be in the processing time as it would be with the runtime, or only the runtime, because they have to share. So they have 15 concurrent processes which compete between each other, and therefore they have to share this. So they need the time of the other processes as well. So it's longer than just the runtime, but they end up earlier than with a batch mode. So shorter processes end up earlier, and longer processes have not so many disadvantages in this preemptive scheduling. It would be interrupted if you have processes which need an interrupt. So for example, interactions with the operator or whatever would directly destroy this mechanism, and therefore it's quite difficult to do that and to create a fair behavior again. And here I can directly show you or explain what is the difference to a real-time operating system. In a real-time operating system, you define, for example, start times or end times, and the real-time operating system must do the scheduling in this competition situation, that the start or this end time is guaranteed. So therefore, there are a lot of interrupts, a lot of processing mechanisms which try to really reach these hard deadlines, and therefore the real-time operating system has a lot of kernel functions, a lot of interrupts, a lot of things which happen directly inside of the kernel, so that it can hold these deadlines. What we did here is a non-real-time operating system, so all processes in this case are used like they were in a social behavior, and they have to share that time. So with this, you can now play. So you can extend the process table, or you can initial situation with priorities, so that processes have priorities. You can select processes first which for example need not so much time, or you can make any decision you want. And if you do this, you have automatically a mechanism to play with other scenarios, for example in a supermarket and with other queues, like in a supermarket with a cashier. And therefore you have a nice tool to simulate the behavior also of real-time scenarios, because at the end it's always a similar situation. And you will see that it's also a similar situation, for example, if you design a fire escape, because people behave in a very similar way, like these queuing mechanisms. And it's very similar if you have the calculation in a CPU, and it's very similar if you have daily situations in a supermarket. So all of these things are similar, and of course simulations are a little bit more difficult in some cases, but they all have to deal with fairness. So what is really fair? If you think in cases of the Titanic, and you have just a number of boats available, and you have to decide who can escape and who not. It's the same here. You have to decide who can process and who not, or is it possible that the resources allow it that everybody processes, or that everybody escapes. In best cases, you have the resources, and therefore it's a tremendous impact if you have more than one core, so if you have more than one CPU available, so that you can split your programs onto these different CPUs. But isn't it nice? So you have now a nice simulation tool where you can play and simulate real-time scenarios. That's it. This was my tutorial for this week. Have a nice time and see you next time in the lesson.